Okay, so I have my components in some sort of order. I'm still going to double check them before I put them in, after what happened last time. So the first three are here, and they're R1, R14 and 16, and they're all 100k. Sorry, if I brought the meter in you'd be able to watch. Okay, so checking these are 100k. Okay, they're 100k, and the first one is R1. And the best way to sort of form these leads is to get hold of them like that and just tease them. Leave them a bit separate because it holds them. So I've already located the position for R1. And I will solder them one at a time for the first couple. Slight pause while I go and clean the soldering iron bit. Okay, damp cloth at the ready. Not used it for a few weeks, so just introduce some solder on both sides of it. Okay, that's one. 14 and 16. 14 is here. No need to put crazy amounts of solder on here. As long as you feel it being absorbed into the holes. There it is. And that's our first resistor value done. Okay, next resistor is 1.8 megs. It's R2. Now this one, my meter won't actually measure, but it's the highest value resistor on the board. So I don't know if the batteries are being lazy. Oh, there we go. That'll do, 1.8 megs. R2. Okay, that was a pause to change glasses. Now I can really see what I'm doing. 20k, R5. With this project, unlike even more than normal projects, it's very important that we get the right resistor values, because if we do transpose two similar value resistors, you're going to end up with inaccurate readings, and that is going to render it pretty useless. Because these are part of the calibration of the device. You don't want a bad oscilloscope. And then this 470K on its own was R40. That should be the last resistor. There it is, right in the middle of the board. And yes, it's a little bit bigger because that's a 1/4 watt one, and most of these are probably 16th watt or 8th watt resistors. But the value of it is the correct value, and that is all that matters. Right. So, number 2, HF chokes. 3 of them, 100 microhenries. I can't measure them. I know they are. There's a little thing there. I know from my knowledge of other components, none of the other components are chokes. So this is L1, L3 and L4. Let's check my recording. Yep. So L1's there. These have got slightly thicker wires as well. L3. Spotted L4 first, so we'll put it in that one. Just trim that excess off. And L3 goes under this resistor pack that I've just made. These wires are heavier and need a little longer to gel. Okay, so those will sit over the top of that without causing any problem by the look of it. Now the 2 diodes are not the same by the look of it, D1 and D2. The reason they look the same is because they're in the same type of package. So one's a 1N5819. And it's not that one. The other one was a 1N4004. And this is input, there we are, so I can see a 5.1 on that, so that's this is D1. The difference could be current consumption, it could be maximum voltage, it could be the voltage drop across it. If you want a diode that works at high speeds, you normally use a Schottky diode, where a normal silicon diode drops 0.6, 0.7 volts. A Schottky diode will drop 0.2, 0.3 volts. So if you check it on the diode range on your meter, it will measure difference. Now I don't know the specification of these. Okay, just as I was about to demonstrate the difference in voltage drop between 2 diodes, the camera battery decided to die, but at least I heard it. So I was able to swap it to the new battery. So this one, the 5189, is it? 5819. That's dropping 186 millivolts, which makes me think it's a high-speed diode. This one is a 1N4004, more traditional. This should drop about 0.7 of a volt. There we go. And that's the difference. So I suspect in this case that D1, the 1N5819, is a high-speed or Schottky diode. And I suspect that due to its position on the board, no, I won't make that judgment, I might be wrong. We'll have a look on the circuit after. So that's D1, and D2 goes up here. And it does actually state on that it's a 1N4004. Carrying out a slightly different job, I suspect. And again, these have got thicker wires still. It seems to have become a convention recently that the anodes, or the positive end of components, are square pads. So a square pad there and a round pad there. It's quite neat actually. I remember designing my first circuit boards and they weren't done on a CAD system. They were done using Litroset tape and ink resist pens, felt tip pens. Nowadays, of course, you can just send them off to certain companies and get them back really quickly. Let me just mark on the thing where I'm up to. So we got all the resistors in, we've got the chokes in, got D1, D2. Next thing is crystal. Again, crystal, fairly unique looking component. It doesn't matter which way round it goes in this case. Sometimes you get 3-pin ones that do matter. And this is just going to vibrate at 8 megahertz, and that will be the timekeeping clock for the whole scope. So the whole accuracy of it is dependent on the accuracy of this crystal. I mentioned when I built the clock, the 6-digit clock kit, that there was some certain people have mentioned that they may not be accurate time-wise. Well, I can't speak for the one that BigLive.com assembled, but the one I've assembled is extremely accurate. It's sat next to the TV, so I can compare it to the news channel in the morning, to their time signal, and additionally to my mobile phone, of course, these days. And it's as spot on as I would expect it to be. The old analog clock I threw away used to gain about a minute a month, so I was happy to throw that away. Crystal. Still got quite a few things to do. J14 USB socket. Now, I'll try and macro in on this. I'll just put the board underneath to let the camera focus on it. If you can see, there's 5 pins in the centre and then 4 tags around the outside. Never actually tested how the focus on this camera works. There we go on the board again. There are 5 holes and then 4 around the outside. And if you had it delivered fairly unmolested, it'll slot in like that. And this one, well, it's barely sitting on the circuit board, so there's nothing at all on this side to hold it. So what I'll do is I'll prop it up on the strip just while I get one tag on. Now, because the casing is made of some sort of metal, yeah, and that is sat flat. that is absolutely sat flat on there. Quick word about plated through holes. Modern circuit boards are plated all the way through the thickness of the board. If you have a look at that hole there, you can see that there is copper plate going through the hole. Don't ask me how they do it, but the point is that when you get a heavier component like this, you can see there I've run the solder until it's coming out the other side. So don't be afraid to run solder into it. That was just to bind it. Now that I have bound it, and again, most important to get the contact on the socket as well as the board. Just let that run in, quite a bit of solder. I'll switch sides so it's not getting too hot. Anybody who's ever replaced a head gasket on a car, be totally aware you do it in a zigzag pattern. Right, I'm just making sure that these pins are through the board. I don't need to run quite so much into these because I don't want them to short out. But you can, when you're doing it, you can see or feel the capillary reaction of the hole drawing the solder into it. Okay, so if you can see on that side, I can see it. I don't know if the camera could see it. You can just see a bit of solder above the pins, those 5 pins, and then on either side. I'm obstructing the light, unfortunately, but you should be able to see the solder on each of those pins on the surface. And because it's going to have a lead connected to it, I won't plug it in now, but because it's going to have a lead connected to it, there could be a bit of flexibility. And the next bit are the tact switches, of which there are 5. So these are momentary contact switches. These are just making contact when your finger's on them. They have 4 pins, but basically those 2 pins are connected together, and then the 2 pins opposing are connected together. And I'll just prove that for you out of interest. I'll put it on the beeper. So if I connect that one, and that one, and that one, and that one, and I'm not going to attempt to do it the other way because it's so fiddly. Right, that's fairly obvious where these go. It would be really difficult to get these in the wrong way, but they do need a little bit of a squeeze. And the way the legs are formed is fantastic because this kink in them will allow it to hold itself in. So you just push them slightly closer together to go in and push it down firmly into the board. The worst thing ever is when you get one of these that's sticking out at an angle. And the case I've got for this, I was quite interested to wonder how you managed to press these with the case on it. And it comes with little extension pieces of plastic, and I think they're really flimsy, but there's no reason why they won't work for the split second that you have to touch each of these. Now once again, I'm going to run the solder through each of these connections so that it provides a bit of stability. It's much easier to solder when the board doesn't move around. So first I'll solder 1 pin on each just to get them to stay put. Well, it's soldering okay, but it's not sucking the solder in like the other ones did. But that's okay because there's going to be so little force on these. I'll solder all the right hand pins first because of the direction they're pointing in. and again I'm moving from one to the next to allow the heat to dissipate before I solder the other pin. Still got quite a lot of small components to go, and we've got a number of capacitors.